Hello children. Now I hope you have completed the previous contents, learning of it and the writing of the contents in the classroom. Right? Now we are entering into a new lesson which is called as magnetism. Right? And we are entering into the part 1 of that lesson. Right? So now in the previous class, what and all the contents we had learned? We have learned about musical instruments, we learned about human ear, and we learned about noise pollution. Right? Now in this content, we are going to learn some introduction about magnets and its classification, what are all the magnetic properties, right? And what is magnetic field and how to trace the magnetic field. So that are the components we are going to see now, right? Now first, what is a magnet? What are magnets? Right? So I hope you are having your textbook in your hand along with your pencil, right? Right. First one, the definitions of magnets. They are the objects of stone, some stone, a very special stone, or some metal, or any other object, but that object should attract these three objects in the main way: iron, nickel, and cobalt. If any substance attract these three objects, and that substance can be called as magnet. Okay. Now, that attraction, no, that substance attracting these three substances, no, iron, nickel, and cobalt, and that attracting property is called as magnetism. Magnetism. In the olden days, this magnetic substance property and magnetic substances were very first discovered in an area called Magnesia. It was found in the Asia Minor region. Right? So that's why it may be interpreted that it was found in that area, no, Magnesia. So it would have got its name magnetism. Right? It's an interpretation only, no experimental evidence or historical evidence is available for it. Right? Next one, where and how we use this magnets? Nowadays in our daily life we use it in refrigerators. On the doors we have when we leave the refrigerator door, it will automatically go and get closed. So it is due to a magnetic property. In computers we use like magnetic chips we use, right? Not like a potato chips, not like our SIM card chips we have, no. Like that we use in the systems and engines, car engines, or even in big industrial machines we use it. Even in cranes we use it, and elevators. Lifts and escalators we use it, right? Now in this point, in the earlier days we can go through the history, right? Chinese were found to be the first to use this magnetic property. They used to travel through sea, right? They used to navigate. To navigate through places, they wanted to find the direction. To find the direction, they used compass. Magnetic compass, have you seen, children? So I will show you a laboratory compass now, right? So this may be the small laboratory type of compass. So this in a bigger format, Chinese were the first to use it, right? So these were the introductory concepts for this magnetism, right? Now we are moving into the next topic, which is called as classification of magnets. There are two types of magnets. One is natural magnets and another one is artificial magnets. What are natural magnets? They are the magnets, but the word itself says it is found in nature. It is found in nature. They are permanent magnets. Permanent means what? They can never lose their magnetic property. Always it will have that attractive property. Right? And where and where we used to find it? We find these natural magnets in sandy deposits area like deserts. Even in our normal residential areas, on the sands, if you wipe this magnet under the sand, soil or sand, right? Some iron filings, you can see that structure in your book at page number 73 under this activity 1. You can see some iron filings, no? So small pieces of iron, right? So they are called as iron filings. So even wherever we have sand filings, a pile of sand, inside that if we just wrap this, right, just move like this, no, then we can, some iron filings will come and get attached to this magnet. right? So wherever we have some sandy deposits, there we can find this natural magnets. So there are some names given to these natural magnets. Some very special names has been given in the book. First one is lodestone, Lodestone, lodestone. It is otherwise called as magnetite. Say the word magnetite, and its chemical name is iron oxide. Right? So there are three names: lodestone, magnetite, or chemical name is iron oxide. And what is another natural magnet? Pyrrhotite, and some people will say that to be pyrrhotite, right? So that is iron sulfide. This name pyrrhotite, Pyrr, always refers to sulfur ores, sulfur name. It goes with sulfur. So it is pyrrhotite is also another natural magnet. And there are some other one, ferrite and coulombite. Ferrite and coulombite. So they are also natural magnets. These are the names for natural magnets. What are they? Lodestone, pyrrhotite, ferrite and coulombite. So they are called natural magnets. And in your book, page number 72, there is one tableau column. Sorry, there is one do you know content. In that they have given some name of ores of the iron. Ore means nothing but children. In petroleum, from petroleum we can get petrol, like that, kerosene and all we are getting, no. So like that, from one main substance we can get this magnet. That main substance we say no children, that is called ore, O-R-E. Like that, some names of ores of iron has been given in that box. Do you know? So read that also. It can be asked in 1 marks. Right, children? Right. Now we move into artificial magnets. The name itself says artificial. Artificial means what? It is a man-made magnet. Right? So it is made in lab or factories. It is a man-made magnet. And see, what we make is very stronger than nature, right? So it is, these magnets are stronger. They can exhibit more magnetic property than natural magnets, right? And now it can be made in different shapes. Some can be bar shapes, right? So these are the bar magnets, right? So one part is this is the magnet what we use in lab. Right, in this we can see this white dot, no children, here. This white dot always refers to North Pole. I'll tell you what are it, right? What is it about? This is North Pole and another end will be automatically South Pole, right? So this is a bar shaped magnet and we have another shape called as, this is U-shaped magnet. It is in the shape of U, no? So it is U-shaped magnet. And this is otherwise called as horseshoe magnet. Horse, no. So it is just like the shoe of the horse, right? The foot of the horse. So it is called as horseshoe magnet or U-shaped magnet. And some magnets will be cylindrical or some magnets will be circular. So there are different types of magnets. So in a major way we use these two shapes of magnets, right? Now coming to the next one. These are made up of iron, nickel, cobalt, steel and alloys of neodymium and samarium. Alloys means what, children? You would have learned in chemistry. It's a mixture of materials, mixture of metals. Right? So how artificial magnets are made? They are made up of iron, nickel, cobalt, steel, alloys of neodymium and samarium. This pronunciation is very important. So please watch the video and get the pronunciation clearly, right? Right. Now we have page number 73. Take that, and there is a tableau column given in that. A difference between natural magnets and artificial magnets. So shall we look into that now? First point I had explained. They are found in nature. They have irregular shapes. And artificial magnets, they are man-made magnets. And they have different shapes and dimensions. And right. Second one also we have just now discussed. Strength of the natural magnet, as it is available in nature, we cannot determine how strong it is. But artificial magnets, how much we require the strength of the magnet. For example, when we use the magnet in the, listen to me now, right? When we use the magnet in the electric bell, our school bell or our calling bells, we need less amount of current only. For that we can use a small amount, small shape of magnet. But when we use in elevators or lift, right, there hey, more number of people will be traveling. In that case, we have to make a big shape of magnet. So depending upon the size, need we can shape the size of the magnets, and strength also we can design accordingly. Right. Next one. These are third point. These are long-lasting magnets, so they are permanent magnets, so they will never lose their property. And next one is time bound. Artificial magnets are time bound. Till how much time we need it. For example, take elevators in our malls and big shops and all, right? Right. When we switch on the elevator only, the elevator will start to work. Right. So whenever it is needed, we can get that work done from the magnets. But permanent magnets, it is not like that. Whether the current is passed or not, it will exhibit its magnetic property. Next one, natural magnets will have less usage only, but artificial magnets, everywhere in our life we use it, starting from our calling bell and school bell. Right? Even in our nowadays boxes, pencil boxes are also coming with the help of this magnets. Yes, no? So wherever we go, use of magnets is around us. Right, the tableau column is very important question. We have 4 points in it, right? So note it down. Next, now we are moving to the next topic, magnetic properties. There are 3 properties we have for magnets, children. One is attractive property, another one is reflective property, third one is directive property. What are the 3? Attractive, reflective and directive property. First one, attractive. See, when I take a magnet, so what magnet is this? Bar magnet. So this is in the shape of a cuboid. Right? So right now this white dot, what I told, it's a north pole. Now I will have one book now with me. I will have another magnet. Just to see these magnets will have 2 poles, 2 ends, children. One end and another end. And these ends are called as poles. P-O-L-E-S. P-O-L-E-S. Right? So now one pole is north and one pole is south. Now you can see here. Now I am having north pole here, this edge. Now I am going to take another pole. Right? Now you see here. It will be more at poles. Right? Now I am bringing another magnet near to it. Right? Now you see. Now let us see how it is getting. See, now how one magnet got attracted to other. See, now it came and got attracted to it, right? Now, see, here at the end only it is getting attracted more. But now, if I do like this, can you see, children? Now when I move to the other side, it is getting attracted in a very lesser way than this pole. See, wherever you go, the pole will get attracted very fastly. But when I move to the other regions, so pole only will get more attracted, right? So what do we conclude from this? Magnetic property will be more at poles. And I am saying this word poles no, children. And these poles always exist in pair only. Pair means what? North pole is there, means south pole will be there. So always this poles will exist as pole, pair, and it cannot exist as a monopole. Single pole we cannot have, right? For example, if I have this magnet, right? So now where is the white dot? Here. So what pole is this? North pole, and this pole is south pole. Now when I am cutting the magnet like this, right? So what will happen? Length of the magnet will be disturbed now. So this is what I had explained, right? So now I am cutting like this. So what will happen? This pole is north. So now when I cut here, what will happen? This pole is south. So when I cut here, this cut one half piece will behave like one magnet, another half piece will behave like another magnet. When I cut here, what will happen? This is north. So automatically the cut end here it will be south. Okay, and this part will come, this cut end, this is south. So automatically this end will become north. So what do you understand from this? Always poles exist in pairs. Clear, children? Right. Next one. Another case now. If I cut like this, it's okay. Now if I cut in the center, right? When I cut like this, right? Now what will happen? Length will not be adjusted. Length will not be changed. So poles will exist as it is, right? So when I cut here at the center, two magnets with same poles at the same size will be available. So what do you understand from this? Always magnet exists as with dipoles, two poles. Monopole will never exist. Okay, right. Now we are moving to the second property, which is called as repulsive property. Repulsive means what? Here, like poles repel each other and unlike poles attract each other. Now I show this now. Right. Now I have a magnet. Where is the north pole? Here. White dot is here only? No. Right. Now I have another magnet here, but white dot is here. So here, this is the north pole, this is south pole. Here, I'll change like this. Then only it will be quite interesting, right? So this is north pole, this is south, this is north and this is south. Now I am trying to move these two, right? Let me see what happens. What happens? They got attracted. How? Here, what pole is here? South, no. What pole was here? North. So they are unlike, different, opposite poles. So unlike poles will attract each other, right? But now I change the case, right? Now I gave the north pole here. Can you see that white dot, children? Right. Now I bring that another white dot here, north and north. Let's see what happens now. Wait. I'm going to play now. See how that magnet is flying away. See, now the magnet is turning around and getting attracted to the poles. Right, now you can see the magnetic property is more at poles, which I had already discussed. Right, but this pole is the north pole. What I brought now you can see it another time. Right, now I have north pole. Here I have north pole. I am bringing another north pole. Right, now I will try with this magnet now. Right, see, I am not doing any magic here. It is its magnet's property. Right, so now you see. So it had fallen down. So if the magnets, opposite poles repel each other. Sorry, like poles repel each other. So like poles repel each other and unlike poles attract each other. So what is this property called as repulsive property? Right. Next one, we are moving to the directive property. Now when I take a magnet, right? Now and when I tie it with a long thread and I suspend it freely with on the tip only if I touch that thread, what will happen, children? The magnet will settle down in north-south direction. That north-south direction, the magnetic north, the north pole of the magnet will denote to the north of the earth, geographical north, and south pole of the magnet will point to the geographic south, right? So that property is called as directive property. A freely suspended magnet will point in north-south direction. NS. North of the magnet will refer to geographical north and south of the magnet will refer to geographical south. Right. Now we are moving to the next topic. What is that magnetic field? Now I have a magnet. Right. Now I have one compass. What is this? Compass. Can you see it, children? Now in this compass you have a needle here. I am bringing it very closer. In that directions are marked here. Right, now if possible try to Just zoom the video and see that. See, now I am bringing the magnet here. Now you can see the fast movement of the needle inside. Can you see? See, now I am moving it, it is turning. Now I see the movement. See, now in the way I am moving, the needle also will move. Can you see it? Right. Now if I am bringing, so see, when I am bringing closer, how much dancing it is. Now when I am moving apart, it will come to rest. Now you see now how it is dancing. See, right. Now till here it can have some distance, right? Now when I bring it to the more distance, it will not have any effect there, right? So around a magnet, till, see, I have another magnet with me, right? Now you see, if I bring here, it gets attracted. Now when here, some attraction will be there, I can feel its movement. Now when I keep this magnet at these two distances, there will not be any force, right? When I increase it, there won't be any force of attraction or repulsion also, right? Now what I am trying to say here is, there will be a space around a magnet till where this magnet can exert its influence, exert its force. That space around a magnet till where it can exert the force, that space is called as magnetic field. Okay, space around a magnet in which its effect or influence is felt. What is the unit of magnetic field? It is Tesla, otherwise we call it as Gauss, Gauss. And 1 Tesla is equal to 10,000 Gauss. Underline these lines in your book. Right? Okay. Now I said to you how you will trace the magnetic field. What will happen now? On the paper, or you have to view this and you have to trace the magnetic field. What you have to do? You have to keep the magnet like this on the board. Right? Now what you have to do? You have to keep the compass, having the compass here. Now you have to keep the compass at one end. Right? So now if the pointer will show in one direction, okay, at that point we have to mark it, right? Put a dot, right? And at that dot we have to keep the magnetic compass. Again that arrow direction we have to point another dot. Like this we have to move and we will get a diagram like this, right? So these magnetic line, this is how we can trace it. We call this another tracing by another word called as mapping. Okay, so when we map this magnetic field, it will start from North Pole and it will end at South Pole, outside the magnet. But inside the magnet, inside these sides, it will start from South Pole and it will end at North Pole. So these points are not in your book, I will give you in the notes. Okay. So what is the mapping rule? What is the nature? Outside the magnet it will start from north and end at south. Inside the magnet it will start from south, go towards north. Okay. Okay. Now when I keep the magnetic compass here, what will happen? When the magnetic compass is near the magnet, the deflection will be more. That's now I showed you, right? So when the compass is very near, or when the magnet is when substances are near the magnet, right? Magnetic substances, the magnetic effect will be more. Like that, here compass is near the magnet means more deflection was there. You observed it now, right? But when I move the magnet away from the compass, the deflection gets reduced. When I move far and far away, the deflection becomes 0. Right? So that is what I have explained here. And this point I have explained to you. Outside the magnet, the magnetic field lines travel from north to south, and inside the magnet it will travel from south to north. Okay, children? So notes I will give you. Copy the notes. Come to the classwork. Come to the class with your completed classwork. And get ready for your class test also. Thank you, children.